Okay, let's talk about Chapter 12, Glaciers. Get my little pen here. Okay, I kind of have a special place in my heart for this chapter because a lot of these photos that are actually I'm going to show you guys are places that I've been and places that I actually took these photos since I used to live in Alaska. So even though it may not be super relevant to Arkansas because there aren't any glaciers here, there are, however, some glacial features that exist in Arkansas, some kind of leftover evidence from the last ice age that we came out of about 12,000 years ago or so. But anyway, so what are glaciers? And, here's the definition. A large, long-lasting mass of ice formed on land that moves downhill under its own weight. And we have also something called glacial terrains, which means that these terrains, these landforms that you see here, are formed by glaciers. There's certain things as a geologist I can look at in this picture and I can tell that, oh, there used to be glaciers here, mainly the fact that this valley has a U shape to it. But anyway, to me though, when I look at a glacier, I look at it in terms of geologic time. Geologic time is something we've, spent some time talking about. And, to us, glaciers are fairly static. They move really, really slowly. But if I were to sort of speed up time, right, let's say that every second, every second is actually a year. If we were able to do that, you would see this glacier moving at a very fast speed, almost like how a river looks. So it is very much geologically speaking, it is very much a river of ice that will erode down mountains and pick up sediment from one place and deposit it somewhere else, just like a river will. It's just, it's just frozen. And it takes a little bit longer for that movement to occur, from that erosion to occur and for the deposition to occur, just because these things are moving so slowly. But they definitely have an effect on the landscape and a little bit different than what normal water does. So, first off, there's two different types of glaciers, main types. What we see today are alpine glaciers. So all these photos that I show you of all these glaciers in the mountains, they're alpine glaciers. And what we had in the past are continental glaciers during the last ice age. I say the past. Antarctica actually is covered in a continental glacier. But these are more ice sheets and they'll act a little bit different, but for the most part it's the same stuff. So how do we get a glacier? How do they form? Do they just poof, freeze out of thin air? Well, no. It's the result, and this is fairly simple, it's the result of snow that falls that never gets melted later on throughout the year. So it actually accumulates over time. It never quite completely goes away. So it can only form where more snow accumulates during the winter than melts away during the warmer parts of the season. And we start to see receding glaciers when the opposite starts to take effect. In a lot of alpine glaciers we see today, the majority of them, by far the majority of them, they're slowly receding and eventually disappearing just because we are dealing with a planet that's warming. So again, you get snow. That snow hits the ground, it starts to get compacted when it's in the ground, it'll kind of form this granular stuff, and when it starts to clump together, we'll actually call that firn. That's not super important, but there it is. And once it sort of crystallizes together, we'll get glacial ice. So where do we find the glaciers on this planet? For the most part, they are in polar regions. And by far in the U.S., Alaska has the most glaciers. This is not a big surprise. Past that is Washington State and some of the higher peaks in Washington. And right now, there's about 10% of the planet that is covered in glacial ice. Now, that was more like 30% during the last ice age. So there were a lot more glaciers during the last ice age. But again, it's only about 30%. That's, that's not 100%. That's not 50%. That's only 30%. So if you remember, we talked about Snowball Earth, the Snowball Earth hypothesis, which was like a super ice age that happened several hundred millions of years ago. Not 10,000 years ago, hundreds of millions of years ago. I think about 650 million years ago was the last one, if I remember right. That was, potentially 100%, where the Earth basically gets a new crust, and it's not rock, it's ice. Maybe. There could have been a small band around the center of the planet that was still water, but we're not sure. Anyway, by far the most of this 10% of glacial ice on the planet is in Antarctica. That shouldn't be too big of a surprise, but 85% is actually quite a big number. So, majority of the ice on this planet is in Antarctica. And if we were to melt all the ice on Antarctica, we'd raise the sea level about 65 meters, give or take probably 10 meters, which is quite a bit. So, I kind of went over this already, snowfall. You compact the snowfall, get the air out of it. It recrystallizes in these little granules. You get firn, and eventually you get glacial ice, and then you've got a glacier. It's somewhat similar if you remember the quartz sandstones we looked at, and then there was also the quartzite. So if you metamorphose a quartz sandstone, you get quartzite. This is kind of like that. Your firn is your sandstone, and glacial ice is sort of your quartzite. Glacial ice is extremely hard. And then gravity causes the glacier to slowly move down slope, and then ablation is the loss of ice on a glacier due to anything, right? If the glacier is falling apart, if it is melting, if it is evaporating, which are all these things, it is ablating. So you see this, here's a small little glacier up here, some remnants, and then you see this melting. This is ablation. This is the glacier ablating. This is me taking a picture through some binoculars using my cell phone. So when you see icebergs, that is evidence of this glacier ablating. These icebergs are falling off this glacier, and you can see the glacier actually continues back up here into this mountain. This is ablation. More icebergs. So we can actually think about, this isn't super important, but we can think about glaciers having a budget, right? So if an advancing glacier, which means it's growing, it has a positive budget, it is getting bigger. A receding glacier, it is losing more than it gains, and it has a negative budget. Now that doesn't mean that the glacier itself is, completely moving backwards. It's still flowing. This ice is still moving this way. It's just that this leading edge is slowly moving backwards more and more and more. These are actually some photos I took. Oh, I didn't take this photo. I'm not this old, but I'm almost that old. But I went and took a picture of a glacier, and then I went online looking for photos of it to see if I could find older pictures of it, because it was kind of at a nice little spot where people would stop and take pictures. And I actually found some, and I kind of want to just sort of fast forward through them back and forth, and I tried to put the pictures in the same location, but this is 1978, this is 2000 something, I wasn't quite sure what the date was on this one. And then there's me, well, that's my fiance, but I'm the one taking a picture, but you can see this is called Bear Glacier, and you can see it receding over time. So it has a depleting budget, or what do we say that, receding budget? Yeah, receding, a negative budget, it's a receding glacier, which most of them these days are. So you can actually see it pulling back over a couple of decades. You can kind of see the tree line here of where it used to be. And we can take a look at this from a map standpoint, because we've covered maps by now, and if you haven't looked at the map stuff by now, go look at it. But we can see this glacier here, and this recent image, this is probably from 2000, well, it says 2019 right there, so maybe 2019. But you can see this glacier coming out, and you can see this little lake is the result. And I tried to guesstimate about how big it was in 1978. And this is about what I came up with based upon that image. And then we can actually look at the topo map of this, so I'll just flip back between these two a couple of times. So we can see this topo map. Now remember what we learned about topo maps is there's some index contours there. You can see how far apart they are. So this is relatively flat. There's not too much steepness over there compared to like right here and right there. But you can see where this glacier would be right here going into this lake. So how do these things move? So it of course occurs due to gravity. There's something called basal sliding, which is the sliding of a glacier over the underlying rock, and it is moving the bedrock, and it is scouring up the bedrock that is underneath it. And it has something called plastics flow. So glacial ice is kind of plasticky, and there's not really a good analogy I've got to that, but it slowly deforms over time just due to all the pressure. It's not completely solid. But given enough time, it will actually flow. Kind of a fun fact is if you look at glass window panes, technically glass will sort of flow over time as well. It's over much longer time periods, but if you look at really, really old window panes, you'll actually see that the bottom of these windows end up being kind of thicker and distorted versus the windows are the parts that are on top of them. And that's just because that glass doesn't have a really good crystalline structure to it. If you remember, volcanic glass is just lava that freezes immediately. But that this stuff can sort of ever so slightly flow over time. If you're ever in really old churches, look at their windows, you'll kind of see what I'm talking about. So we have this plastic zone, which is kind of in the bottom part due to all the pressure. And then we have this rigid zone, which is more near the top. There's less pressure. And the center part of the glacier actually moves faster than the outer edges of the glacier. And if cracks form, we call them crevasses. These are why it's really dangerous to go hiking around on the glacier, because you can easily step on some snow and then fall into a crevasse you didn't even know was there. This is one of the reasons I've hardly ever hiked on glaciers, because I'm just too scared of this. Okay, moving on. So different glaciers do move at different speeds. Some will move at up to 15 meters per day, and some are just a few millimeters. But if you remember me talking in plate tectonics, a tectonic plate will move just a few centimeters, actually about this far per year. And these things, even at their slowest, are moving this far, in a day or a week, versus tectonic plates which take that long to move in a year. So slow to our eyes, but geologically speaking, fairly quick, and some of them extremely quick. So again, there's kind of that image blown up, and kind of what I want to show here are these little holes. If you were to drill a whole bunch of holes going straight across a glacier and let them move over time, this is what would happen: is your stuff to the outside would move slower than the stuff in the middle, and they would get bent as they go down. Areas where you kind of have a bend or you have an increase in the relief here of the slope, that's kind of when these crevasses will form as you kind of bend the glacier as it goes down. Now, and one of the real reasons we care about glaciers as geologists, because it's ice. Ice is boring. We want to talk about rocks. That's not true. Ice is important. But anyway, glaciers erode the underlying rock by plucking the rocks out, right? So in warmer seasons, you'll get water that will actually melt underneath these glaciers, potentially. Will get into these little cracks, and they'll freeze because of frost wedging, if you remember from weathering and erosion. And then the glacier is kind of able to pop these rocks out of there because of that frost wedging, or just because of the pressure. But also, they will polish the bedrock. So in areas that have had recent glaciation, you can kind of see this polishing feature along rocks, and you can know that, oh, there used to be a glacier here, and it's polishing this rock. And all that stuff I just said. So, landscapes. This is important. This right here is important. I will ask you questions about this. This is such a fun little question to ask, and it's super simple. I will definitely ask you about this. So, glaciated valleys or recently glaciated valleys will have a U shape to them versus not glaciated valleys, valleys that are controlled by streams and running water, they will have a V shape to them. So here in Arkansas, we've got V-shaped valleys. And if you wonder, did Arkansas used to have glaciers, you can look at the topo maps of all around Arkansas, and you can look to see if you can find U-shaped valleys, and you don't find any. Kind of looks like a face. Anyway, so there's a bunch of different features we can get. These three I'm going to ask you guys to identify. I'll go through them here in a little bit. But some features we can have are something called hanging valleys. I'll look at those in a little bit. And then these truncated spurs, which are basically ridges that have this triangular edge to them, and I'll look at that in a second. But the first thing is U-shaped valley. This is up on the mountains up near Anchorage, Alaska. You can hike up to this. It's called Flat Top. But you notice there is a U-shaped valley. And here we have a glaciated valley, right? Or before glaciation or long after glaciation, and they're dominated by these V shapes. Versus glaciated, where these glaciers will carve these U-shaped valleys, and they'll do it all over the place. And they'll create these things called cirques back here, which are these bowl-shaped depressions at the very back. And they'll create these mountains called horns, and then these long ridges called arêtes. And horns, and these glaciers will also carve off the front end of these arêtes and create these truncated spurs. But I'm not super. I don't need you to memorize that, but I definitely want you to know these things, and that these things are called cirques. But after glaciation, streams will come back, right? The glaciers go and recede, and they'll slowly turn these valleys back into V shapes. In fact, I took a picture once in southern Alaska. I forget where. In fact, I don't know exactly where this is. I was flying out to Dutch Harbor, but I spotted this and kind of took a picture of it, and I can see glacial features here. I can see these cirques, these kind of bowl-shaped valleys, or these bowl-shaped at the back of these valleys. But then I also noticed that there's these streams. You can see one stream kind of running through here, and it's a little more V-shaped back here. It's not quite as U-shaped anymore. So in this area, during the last ice age, this was all glaciated. You would have had a big old glacier coming out of here, and you would have had icebergs breaking off out into here. But that's all gone now. It's all warmed up, and so now we've got all these cirques and that are kind of left over, but streams are starting to take over again and make things V-shaped. Honestly, give this another 50,000 years, maybe a little less, and it'd be hard to tell that glaciers were here to begin with. So let's look a little more closely at some of these features. I'll start with cirques. The reason I'm kind of also going to lean into these is I'm going to ask you guys to kind of do a mapping assignment. We're going to look at topo maps, and we're going to look for these features on a topographic map, so pay attention. So here's a cirque. You can see that bowl shape, right? You see it? Nice big bowl-shaped feature there. You don't find this in Arkansas. This kind of features, they don't really exist. If they do, it's sort of an accident. Here's a photograph I took from a plane. Just take a second, look at it, see if you can identify any cirques. Should be one obvious one. Right there. You see the glacier here, right? It's coming out here into the water. But it's starting up here, all this snowfall up here high in the mountains, and it's compacting into that fern and then turning into glacial ice, and then the glacier is moving down here and melting, and look, icebergs. And there's another one up here. So there's another cirque. In addition to cirques, we also have arites or horns. Arites are basically the sharp ridges between the glacial valleys, and the horns are these peaks that are normally kind of have three ridges coming off of them, but sometimes they can have more than that, but a lot of times you see them with three. So back to this same image, we've got our cirque there, So let's start with an arete. Where's an arete? A big long ridge. There's a big long ridge. Fairly obvious. What about here? It's kind of an arete along that way, a big long ridge, the glacier on each side that end up coming together. And look, these two glaciers that come out of here, and one that comes out of here, looks like another one comes out of this way. Between these two, you can see they're scouring off this mountain right here, and they're pulling all that sediment away from the mountain, and this is that sediment stuck between those two glaciers. So here, we're looking down an arete, this big long ridge. In fact, there's a hiking trail that goes along this. I was standing up here once, hanging out with Danielle, my fiance, if you haven't met her. And there's every now and then these people that are just insane outdoor, super athletic folks will just come jogging along like it's nothing. And you realize they were jogging along this ridge. These trail runners. Maybe some of you guys are into that. If you ever go to Anchorage, there's lots of trail running. Be careful though, there's bears, and sometimes they get people. I'm not joking. So here, this is a Klutna Lake. There's sort of an arete here, but I see more of one back there. Let's look at this from a topographic map standpoint. We're going to look at this from the sky. Boom. So we're actually back here looking this way at this peak. You see that peak there? I'll go back. So there's that peak right there. And there it is up here. So you can see these aretes that are coming off of it, right? You can see these ridges. And then this by itself is a horn. Three ridges meet, and you got yourself a nice horn. Take a second. Do you notice any others in this picture? That's right. There's one down here. You can see an arete, little arete coming off that way, a little bit on there, a little bit on there. But definitely a nice horn there, and maybe kind of one right there too. Kind of one right there too. And then you can see all these long ridges. You don't see these type of topographic features around here in Arkansas. It's much more dendritic. Also, now that we're looking at topo maps, remember the rule of V's? That lines V upstream. Well, there's your contour line V'ing upstream. So I know by looking at this that this stream is flowing that way. So, do you see any horns in this picture? Take a second. I mean, I guess a lot of these little peaks, a lot of these little things, you could try to argue, I guess that's a horn, that's kind of a horn, okay, that's a horn too. But for the most part, we're kind of looking for the bigger ones, and the big one in this picture is probably this one way back here. And there's definitely another one right there. And another one, right there. Is that the same place? That's the same place. I wonder if that's a different flight or the same flight. So looking a little closely, you can kind of see this horn right there. I think I drew a circle. Yeah, there's a circle. And then that bigger one up there again. But again, you can see this nice big bowl here of this cirque. Hey, remember that how I pointed out that sediment before? There's a glacier coming down here. There's a glacier coming down here. And look, they're scouring off this mountain right here and creating this sediment. This has a name. We'll talk about this in a little bit. Hanging valleys. So sometimes you'll get these hanging valleys. This is in Yosemite, I believe. But you can see this U-shaped here. It still exists. And so you had a glacier that was in this valley down here that was moving off that way, and it scoured off this area, but you would have had another glacier that kind of met up with it, in this area. So there's actually, back to this image, there's a little bit of a hanging valley. It's kind of a half hanging valley in this image, and I'm just going to zoom in a little bit to try and point it out. So there's a cirque right here, and there's a little bit of a leftover glacier that's coming out this way, but there's a hanging valley just barely kind of right in here. And if I look at it from a topographic map standpoint, just go between those two, so you see that? So there's the cirque back there. That little glacier we're looking at probably sticks out like that. See that? But you'll notice that these contour lines are a little bit, spaced out up here. But as we get to about right in here somewhere, they get really close together. So it's kind of a hanging valley, just barely. Just barely. So here, you're standing at the back of a cirque. Some little glacial lakes, we'll talk about those in a minute. And again, we'll look at this from a topographic map standpoint. So there's the topographic map. You were standing up here in that picture, and you're looking that way. That way. See that? So there's kind of what it looks like topographically. Those ponds down there. See that? A couple of ponds. Boop, boop. I guess there's another one here, and maybe another one there that's not on the map. And there's Summit Lake. Summit Lake. So, you see any other features on here? Let me back up. See any other features on here? If we were in class, I'd be throwing a laser pointer around to you guys and having you point out the different features. But take a second. Do you see any cirques? Where are the cirques? There's one right there. Yes. What else? Okay, there's another one right there. Kind of one right there. Maybe. Yeah, maybe one right there. Definitely one back here. If you look at this, I mean, it's almost like they grow together. Sometimes that happens. There's one back here, kind of one right here. And then you have all these aretes all over the place. And then you've got horns, and there's a nice horn right there. There's definitely a good one right there. So you can kind of see all these features. But hey, look at these streams here. So the glaciers are long gone now, but you can see how the stream is starting to carve back into these valleys. You can see how that's depressed down there. So, back to geology. The sediment that comes out of glaciers, so the glaciers are bringing all this sediment down, and when it reaches the end of the glacier, especially as they recede, you end up getting glacial till, which is just this really unconsolidated mass of dirt and rocks, and it's poorly sorted, it's not well rounded, and it's not stuck together at all, it's not compacted. It's just all this stuff dumped right there. Again, not sorted, not rounded. There's no graded bedding. If you remember what graded bedding was, or if maybe you don't, it's where you'll get the larger pieces at the bottom, and you'll get medium pieces on top of that, and then it'll get smaller and smaller as you go up. We find these kind of deposits with rivers, where big stuff at the bottom, and medium-sized stuff, and smaller stuff. That's graded bedding. With glacial till, you don't see that. It doesn't get sorted like that. So here's kind of what it looks like. It's just all this material in and around here, different sizes of stuff. Mostly jagged material. Some can be rounded, but just poorly sorted. So the till can sort of be organized or pushed around into what we call moraines. This is important. And there are lateral moraines, there's medial moraines, and there's in moraines, and they're basically what they sound like. So we've got, in fact, here's more, but so lateral moraines are the ones that we see on the sides of the valleys. The medial moraines are the ones that we find between the ice, between these glaciers. They're the ones that kind of pointed out earlier. The end moraines are the stuff at the very front end of a glacier, so end moraine. Then we can have some, as the glaciers move back and forth, we can have other moraines at the end. But for the most part, I don't want to say that. I will tell you whether I want you to memorize all of these or not. Probably not, but I might. It depends. But each individual class I teach, sometimes I have you guys memorize these, sometimes I don't. But I definitely want you to know what a moraine is. They're important. So here, we see a glacier moving down this way, see another one moving down this way. And we can see when they come together, right? There's that medial moraine. Is that right? Medial? Yep, medial. Medial moraine right there in between them, being scoured off between these two mountains. I'm going to zoom in a little bit. You can also see the lateral moraines. There's actually a ridge of material right there when this glacier was bigger on the edge of it. In fact, now that I'm letting my eyes adjust, there's an even bigger one right there. Big, large lateral moraine of dirt and material that these glaciers were pushing around. So there's that blown up. Medial moraines, lateral moraines. So lateral moraine turns into medial moraine. Medial moraines that are coming from upslope. And then these other end moraines. So here we actually see, well, first take a look at this, what's going on. There's a glacier coming out here, right? It's melting. We get a glacial lake here, and then there's a river with lots of sediment in it that's flowing over here. Let's look at this as a topographic map. What do you notice? The moraines are creating a natural dam for this lake as the glacier recedes. And you fill it up enough and it'll actually break past the glacier. But this whole area, this is dominated by this glacier and what it's been doing to the sediment that it's bringing down from up here. So we also have outwash, which is the sediment departed over time by large amounts of meltwater flowing over, beneath, and away from the ice at the end of the glacier. So basically the outwash is moving around the till. So once water gets a hold of the till, we start calling it outwash. And we'll see a braided channel drainage pattern because of this, because there's so much sediment. Tons and tons and tons of sediment. And so we get braided channels instead of the meandering streams that we see around here in Arkansas. That we mostly see around here in Arkansas. So here's evidence of that. There's all sorts of sediment in this river, and we can kind of see how braided this is, right? Hence the name braided stream or braided river. I like drawing. And that this forms because of there's just so much sediment. When you put tons of sediment into a river system, it will develop this kind of braided stream system. And you see this in places where there's lots of glaciers with lots of till and outwash coming out of them. So we see rivers like this a lot up in Alaska versus, I mean, not all of them. So they start to meander eventually when they kind of lose some of that sediment load. But yeah. So other features that we'll see, you see these little teardrop shaped looking forms. These are called drumlins. And they're just kind of these little mounds that are left over from glaciers that used to be there, and they've been scraped over by the glacier, and it kind of ended up forming that little teardrop shaped. And in the outwash, we will see these other features there. We'll see eskers, which are these little sinuous ridges. We'll see kettles, which are these little kettle lakes. That one is more important than the others. We see kames, which are low glacial mounds just from water flowing. Then the drumlins, which are larger from the scouring I just mentioned to you. And then we'll see varves. And varves are sediment deposits from glacial lakes. And it's what you're seeing over here, just this back and forth, and it's just this seasonal changes. And I'll probably have you guys watch a video, if we haven't already, about the huge glacial lakes that used to exist in parts of North America when the glaciers receded. In fact, there's still some around. They're called the Great Lakes. There's a little kame. There's all the till around here. There's a little kettle lake. And you're wondering, how do I tell the difference between these and a drumlin? Don't worry about it. I'm not too concerned that you know the difference between that. So in some of these other photos, back up in the cirques, where these glaciers were, we'd see little lakes that were left over up there. Those are not kettle lakes. These kettle lakes are the result of the outwash. These little lakes up here are called tarns. So I want you to know the difference kind of between these two. So the tarns, they're in bedrock at the back end of where these glaciers started. The kettles are in the sediment and all the outwash. The tarns are an erosional feature from that glacier scouring out the top of the mountain. The kettles are the result of the depositing of the sediment. The tarns are way up in the mountains. The kettles are down in the lowlands where there's huge streams. Around tarns, you will find horns and cirques, especially cirques. They are like in the cirques, and then of course the aretes. And then in the kettles, you'll find moraines nearby and drumlins and that kind of thing. And in the tarns, you'll find them in high relief areas, versus the kettles are more in low relief areas. And there's that varves picture again. Probably going to have you guys watch a video that kind of deals with this stuff. I've kind of mentioned that we had a recent ice age. We've talked about this in class. That's kind of what this is saying. There is plenty of evidence, as we've kind of been looking at. We can see evidence that glaciers used to exist. Some of the other things we see besides the moraines is we'll see special lake basins that are kind of the leftovers of where these glaciers were, like these. I'll blow this up to talk about it. That one looks better. So I mentioned that there used to be large glacial lakes in the U.S., and probably the most famous ones are the Great Lakes. So these are leftover glacial lakes. So we used to have a big ice sheet that came down this far during the last ice age. In fact, I think it came a little bit farther, something like that. But as it receded, it left these moraines there. So all those little squiggly lines are moraines that still exist that you can go walk around on and find. And then we also had this huge lake up here called Glacial Lake Agassiz. And I'll show you guys a couple of videos if I don't ask me. Regarding this lake. This lake may have caused the extinction coming out of the last ice age, and it's not because, how does that happen? Well, because it was dammed up by ice to begin with, and then when it emptied out either down this way or perhaps out this way, and dumped a ton of fresh water into the Gulf of Mexico, or Gulf of Mexico, the Atlantic. And that would have messed with the currents, the circulating currents that are out here, the thermohaline currents that typically come up from the Gulf of Mexico or from from the equatorial area, and they head off up here and eventually over to Europe. And if you dump, part of the reason that current exists is because it comes up to the north, it gets a little fresher, and it kind of creates a cycle due to melting ice. Well, if you throw a whole bunch of fresh water in all of a sudden, you can kind of mess it up and slow it down, and that can kind of cause a big old shift in climate. So the draining of this lake may have caused that. There were other lakes over here. There was the glacial Lake Missoula, which filled up and then broke out and flowed this way, and it did it multiple times. And of course, the Great Salt Lake used to be a lot bigger. And there's this Lake Lahontan. Oof, I'm sure I butchered that. I don't know anything about that one, but I know quite a bit about this one because I've been up here. So here's a picture of that. These are called the Scablands, and it's evidence of when these huge glaciers, and I'm kind of talking about the videos I said I was going to show you, but it's when evidence of these glacial lakes were released, and you had these gigantic mega floods. And if you look at this for a second, you start to realize that, hey, look at these little hills. They kind of look like ripples, don't they? And that's because they are ripples. And there's what I assume is a tractor. So gigantic ripples from a giant mega flood that would have flown down this way. And there's plenty of other evidence in these Scablands. They kind of live up to their name. If you drive around them and look enough, you'll see evidence of this giant flood. And I say flood, it's not that the water just rose up. It's that it came gushing down this valley, a massive torrent of water, and it did it over and over again as this lake filled up and then got too full, broke out of its ice dam, and filled back up again, and rinse and repeat. So during the last ice age, here's kind of where the northern hemisphere, where the extent of the ice was, and it was very much kind of a North American phenomenon in a big way. Europe was, a little less icy, probably thanks to that current I mentioned, the Gulf Stream. But we had a lot more ice that came down here, and so what did that look like around here? So I like to think about, what did Arkansas used to look like in a lot of these situations. So here's a great little map that kind of shows what was going on. So, today, here's our modern coastline. Well, during the last ice age, there was a lot more H2O on the surface of the planet thanks to these glaciers, so sea levels dropped. So the coastline was actually much farther out into the ocean, to the bane of archaeologists. I'll talk about that in a second. But when these glaciers were receding, they were dumping all sorts of sediment and water as they receded. It would have been a wetter kind of world as these things were receding. The rivers like the Mississippi River would have been insanely large, and they wouldn't have been meandering, they would have been braided. And around here, we would have seen these kinds of climates. So we can go look at those types of modern climates today. And so here in Arkansas, if you go walking into the forest, you'll see kind of a temperate forest, right? You'll see oak trees and hardwoods and that. However, if you go back to last ice age, you would have seen more pine trees. It would have been wetter. It would have looked a lot more like the Pacific Northwest if you've been to Washington State or anything like that. And again, the rivers would have been far more braided, have a lot more sediment coming out of them. And it would have just been cold. So honestly, if you've ever been to Washington State and you go on a hike, I encourage you to go on a hike, go out into the woods, and imagine that this is what Arkansas used to look like just about 12,000 years ago. Actually, less than that. We're coming out of the Ice Age. This is what it looked like just a few thousand years ago. So another phenomenon that happens when you remove these glaciers, something called crustal rebound. And if those of you that are my age, you might remember there was a kind of an earthquake that made the news. It happened, where did it happen? It happened somewhere along the East Coast. But the entire East Coast felt the earthquake. It was something like a 5.0 or something, or a 5.2. It was not that big of an earthquake, because if you're from California, you say, oh, 5.0, huh, that's nothing, man. Like, what are you talking about? Like, we get such big earthquakes out here. Well, the eastern seaboard, all the rocks around there are much older, they are flatter, and not as fractured. California kind of acts like a little bowl and insulates the rest of the area when they have earthquakes. Those waves don't travel very far. They get messed up. However, when you have an earthquake over here, those waves can travel really far. They're unimpeded. It's kind of like the difference of slamming your hand down on a mattress versus slamming your hand down on a table. You might not feel it so much at the end of the mattress. However, at the end of the table, you definitely feel it. And I'll talk more about this when we get into earthquakes. But anyway, that earthquake happened because of crustal rebound. You used to have miles of glaciers all over this area, and they've melted. But they provided a whole lot of weight. They were massive. They pushed down on the rocks, and you remove them quickly, right? These left within a couple thousand years, and now all of a sudden the crust is rebounding a little bit, and that's what's causing some of these earthquakes that we see in areas that normally don't have earthquakes. And we can actually measure this uplift. So we've talked about GPS and GIS, and if we haven't yet, then we will. But we can track the movement of this crustal rebound. We can measure it using GPS receivers. So the faster rebound is up here in the more northern latitudes where you had more ice, and slower down here. But we're talking about, 10 millimeters a year. That's a centimeter per year. The ground is going up 10 centimeters a year in these areas. But kind of wild. So another thing you can get, so evidence of glaciation. So this is a glacial till that has been solidified. Big word. So it's no longer a glacial till, right? It's not just dirt and rocks and loose sediment. It's been compacted and preserved. So you can look at this and go, oh man, this is evidence of past glaciation. And you don't get this stuff forming, within within a few thousand years. This is probably a rock that is millions and millions and millions of years old, and evidence of glaciation from a long time ago. And we call these things tillites. And so these tillites are some of the pieces of evidence that we can find that give us, lend credence to things like the snowball Earth hypothesis and other time periods in Earth's history where we've seen glaciation. Like snowball Earth. Yay, snowball Earth. Yay. Cool thing. We'll talk a little bit about climate change, but we can see in Earth's past that there have been time periods where it has been colder, and we have likely had large glaciation events. How do we know this? Mostly isotopes. And I talked about isotopes at the beginning of class. But basically, you can look at the oxygen isotopes in rocks and in fossils, and there's some other things besides isotopes, but this is kind of how we know where things are warmer and colder. And notice that there aren't numbers along this axis. It is really hard to put a number on how cold it was or how warm it was. We can have some good estimates, but generally we just know how relatively colder it was or how relatively warmer it was. However, there are new methods, new isotopic methods that are coming out to where we can look back in the past. And one of the methods I worked on was we could literally put we could look at a fossil and look at a combination of isotopes and put a plus or minus 2 degrees Celsius on stuff like this. So in the coming future, as more research is done, you'll start to see numbers on these things, and we'll know just how cold it was during snowball Earth or during this colder period before the Permian. Yeah, anyway. So I think that's all I've got for that. Hopefully you learned something.